All right, so we are back again, and what we want to do is to demonstrate the concept of co-integration, how it works, and I'm going to do that in Python. But I prefer to work with collaboratory. On collaboratory, it's easier. You don't need to download packages and all the other drama that is involved with Anaconda and Jupiter and everything. So I'm going to try and be fast with this concept. So what is it that we are trying to achieve? What is it? What is our goal here? So we are trying to demonstrate the concept of co-integration, which, if you remember, we said uh, when you have got, we use it in time series analysis to identify long-term relationships between variables. That's what we are trying to do, because you want to see what's going to happen if you have got data, closing price data for stock A and closing price data for stock B. So still it's a pair. We are still looking at a pair of stocks, and so the basic idea is that you need to have two time series trends that have trends, and then the linear combination of this series may be stationary, indicating a long-term relationship. That is the idea of co-integration. So first of all, you need to choose two time series, then you plot them, and make a visual inspection. So let me just write here to say choose two time series, and that's the first thing that you want to do. Then number two, make a visual inspection of just by plotting, right? So you plot, and then number three, the next thing, now this is why we are here. The idea that you want to test for stationarity. Test for stationarity. So when you test for stationarity, what are you doing? When you test for stationarity, you are checking whether each time series is stationary or not. The past data, does it influence what is going to happen next? So that's what you're trying to check. And we normally use the ADF, the augmented Dickey-Fuller test. We have got the KPSS test as well, the Kwiatkowski Philip Schmid Shin test. But then we are going to restrict ourselves to the ADF, which is a little bit common. And then what else do you want to do? Then we need to then calculate the co-integration test. So for 4, calculate the co-integration test. And once we do that, then that's when we run the regression. All right. So we are going to regress one variable on the other so that we get the residuals. And then in the residuals, we test for stationarity. All right. Okay. So we say test for stationarity in the residuals of the regression analysis. All right. And then we interpret the results. That will be the last thing. Interpret the results. Okay. This is what we want to do. So the reason why we are here is because we are going to be doing it in Python. Let's just call this untitled co-integration, right? Co-integration. That's what we want to call this file. All right. So how do we start? Like we said, we choose two time series, but we are going to need some statistics tools. All right. And this example is just a basic example. Basically, we're going to need statistics tools so that we actually, and the plot, so matplotlib, we're going to need it. And we are also going to need to import the ADF package, the augmented Dickey-Fuller package. It's part of the statistics tools. So let's create some artificial data. That's what we want to do. Let's create some artificial data, and then after that, so we import the libraries, then we generate some example data, and then we plot the data to visualize it. That's what we want to do. And to do that, I'm not going to write a lot of code. I ran the code here and I saw that it's working. So I would rather copy and paste the code and tell you what is happening here. So these are the necessary libraries that I was talking about. I need NumPy. We know NumPy. It's part of the pandas library for numerical operations. Pandas is for data manipulation. NumPy is for numerical operations. Stats models for statistical modeling, and matplotlib for plotting. So we need to include matplotlib here as well. I think. Let me just add it there, and not there, but rather here. All right. So these are running, this is running, and if there is a green tick there, then it means we are good to go. It is imported, but I'm not so sure if it is registered matplotlib. Okay, now it is registered matplotlib. Now the next thing is I'm going to generate data using some random seed. So we just this is just random data that we are going to um, just to run there and see how far we are going to go. So that's what we have. Um, so what we do is the NP random seed 42, it sets the seed for the random number generator provided by NumPy, right? And if we set a seed, it ensures that the random numbers generated by the program are reproducible. In other words, if you run the same code with the same seed, you will get the same sequence. Because if you don't put a random seed, then it's just going to give you another set of different numbers. So you want to make sure that the random numbers generated by the program are reproducible. Right. All right, so that's what we have got. So we have generated our data here, and we can actually view this data if you want. We can just write X, capital letter X, and run this, and you can see some data is coming out. We can also do the same for Y, but we don't want to. We don't want to do that. All right. So now after doing this, what do we want to do? We want to plot just to visualize. Visualizing is better because it will show you what the situation is. So let me just say plot visualize. Plot to visualize. And you put, so the plot here is we've got our x-axis, the x-axis is going to be labeled X, and the y-axis is going to be labeled stock Y. No, the graph itself. So this is then we've got a legend that we've got, and then we've got the plot show. So there is time. As time moves, what will be happening? All right, and then we get something like this. So we have got xy, but then we've got time here, and then we've got the value over here. So this is the value, could be the prices or something, returns or anything. But what you then have here is the time. So this graph is poor graph. We could add more and then just make sure that we have got time clearly written on the other side and all the other stuff. But let's not focus on that because we are out of time. So this now is just a visualization. And then if you ask yourself, like, is there co-integration? You can't really tell out of under these circumstances if there is co-integration. You can even conclude and say there is no co-integration because the other graph is going that way and the other graph is going that way. But that's not how it works. That's not how it's done. You have to check for stationarity, and then after interpreting the results of stationarity, then you proceed to your regression where you run the co-integration test. So to check for stationarity, we are going to um, just say, I can quickly say AD Fuller, augmented Dick Fuller for X, right? Like this. And if I run this, it must give me this result that I've got here. All right. And I also run but then I would rather do it with some name here. That's what I would prefer, so that everything makes sense. So let me just say check for stationarity, then result X, AD Fuller for X, result Y, AD Fuller for Y. And then I want these results to be printed in a nice way. I want to see the p-value. Okay. In R, this is pretty much straightforward. Actually, it's not like you put in a request. You just write ADF X and then you get the results. But we are not in R, we are in Python. So this is what we have. We've got p-value is equals to 0.97, 0.93. And under these circumstances, we are seeing that the p-value is above our confidence interval of 0.05, and we can sort of like have challenges with the interpretation, and that's not what we are trying to work on here, because remember we said we are interested in uh, we are interested in the ADF of the regression, all right, of the residuals. That's the most interesting ADF that we are interested in. So that's what we want to check, if there is evidence in favor of co-integration or there is no evidence in favor of co-integration, all right. And you realize that the negative ADF static for variable y might be due to a slight trend in the data. But as I said again, as I've been saying for some time, the co-integration test, it focuses on residuals. So it is very, very important for us to move on to that part. Okay. We need to move on to that part and see what's going on. Now, this is the most important part. The part where we run the co-integration test. So this is the part where we run the co-integration test. And to run the co-integration test, we need to be very, very careful. And I'm going to try and explain every line of code that I am going to be using here. So first of all, what we are trying to do, if you, I think I need to add more text here. I need to say, mostly we are dealing with y is equals to mx plus c. All right, this is linear regression, right? And that's the thing that we are trying to do. So there is a constant here, then there is a variable x here. This is the independent variable, and then there is a dependent variable. That's what we are trying to do. So in other words, in our case, we have got to deal with y is equals to alpha plus beta x plus some error term. This. That's what we are trying to do. That's what we are dealing with here. So this is the equation, the regression model, and the constant term alpha is added to the independent variable x. And how do we add that? Well, we are adding it to x. So let me just say, if we are adding a so we are going to say add a constant term to variable x, and the constant term is appended or is added to the constant x in this particular way. Right. And then we create an ordinary least squares regression model. So in Python, to do that, you simply tell Python that, look, the model that I want to work with. So you say model, model is equals to SM or LS, so ordinary least squares YX. And you start with the dependent variable and then finish with the independent variable. Then after that, this because this creates an ordinary least squares regression model, and in this context, um, remember that x is already added with a constant term, so it comes with the constant term. That's what is beautiful about this code that we can see here. Then you now need to fit the regression model to the data that you have got. And well, how you do that is you simply say, I want to fit regression model to the data. So you use model fit there. All right. And if you run this, let's see what happens if we run this. So this just runs. There are no results that we get. There is no output that we get. And the first thing that you might want, because we said, look, with the co-integration test, we are more interested in the residuals. So what you need to do is to extract the residuals from the regression. So to do that, we are going to say extract the residuals from the regression, and now you've got your residuals. So residuals, remember residuals are the difference that we find between what is and what actually is coming out. So that's a treatment, the difference between the actual values of y and the values predicted by the regression model. So these residuals are then used in the subsequent test step to test for stationarity and consequently co-integration. So let's run this so that we also capture our residuals. So you create new code there, a new cell for code. So now we have got our residuals, all right? And it's a variable on its own. And residuals contains the residuals obtained from the OLS regression, and these are, we have now to subject these to ADF, right? Augmented Dickey-Fuller test to check for stationarity, and by extension, co-integration. All right, we want to check whether or not this is stationary. So um, some people can say, what is stationarity really? Because it is why it is appearing more and more, and it's very important. And I can tell you that this is a statistical property which is very, very important, whereby we are checking whether a time series is remaining constant over time, right? In other words, if we've got a stationary time series, it is one whose statistical properties such as the mean, the variance, the autocorrelation, those they must not change with time, right? They must remain constant to a certain point. And we've got types of stationarity like the strict stationarity, we've got the weak stationarity, and in most cases, we use the Dickey-Fuller augmented test. We've got like the Enko-Granger two-step procedure, which involves actually checking for stationarity of the residuals obtained and then regressing, those things. But that's not what we are concerned about. We are concerned about now, um, can we run the Dickey-Fuller stationarity test for the residuals, and this is going to give us some interesting results. All right, let's see if we have got. So now we've got results, core integration. Then we are running the ADF on the residuals, these residuals that we got here, that we extracted from our regression. And if we do that, we are now getting that the p-value here is, can you see that it's 10 to the power of minus 17. So from this, we get that our p-value is very small, and it means that we can, the now, because the now hypothesis, I think it's very, very important to mention the now hypothesis in this case. H naught says, all right, so the now hypothesis says there is, so the p-value, or there is a unit root in the residuals, right? There is a unit root in the residuals. And then the alternative hypothesis says otherwise, right? So the alternative hypothesis says otherwise. So if since we are getting the a law which is a low p-value for the residuals, which is extremely low under these circumstances, we can actually reject the null hypothesis of a unit root in the residuals. And this provide evidence in favor of co-integration between two variables, x and y. And that makes us happy. So if what we are simply saying is that if our result was going to be, say, our p-value is 0.95, then this was going to be greater than 0.05. And then we're going to fail to reject the null hypothesis, and further investigations were going to be needed. But because our p-value is 0.000000000, and for 17 times we can go with the zeros until we get to 5, 1, 8, 4, and so on, then this is less than 0.05. And in that respect, we fail to, we reject the null hypothesis of a unit root in the residuals. All right, so that's what we were doing here. And in this, in light of this now, we are happy that we've managed to show the stationarity uh, we've managed to show the stationarity of the residuals. And what we do now is what we did in the code above was adding a constant term to x, then run the ordinary we ran our regression, and then we saw the we applied the ADF test, and we interpreted the results. So the p-value for the residuals, which is below 0.05, is telling us that co-integration exists. So there is co-integration. It's evidence of a long-term relationship between x and y. Otherwise, it was going to be something else different. So we have got all this. We did all these things. And what you can also do is to write some loop that can tell us what the results are saying. So let me just add that extra part. Let me say text, not text. I want code, the loop that interprets the results. And here we are actually getting that co-integration exists if the results for co-integration, which is the p result, is less than 0.05. All right, guys, so we did all that. We are happy. And we are now going to move on to something else different, because it is very important for us to talk about this co-integration, because it's a term that is going to appear more and more in the discussions that we are going to have.